Hi everybody, and welcome to a discussion with Twesh Upadhyaya regarding non-commuting conserved charges in quantum thermodynamics and beyond. I hope you enjoy our discussion. We have the paper on the screen, and I think it would be great if you could provide some background to kick us off with why you published this paper to begin with. What was sort of the motivation for examining this?
Yeah. So in thermodynamics, we're often interested in this idea of systems exchanging something with other systems or other environments. So in a very simple case, one of the kind of motivations that started thermodynamics in the first place, we have, say, an engine exchanging energy with a hot and a cold environment. So in a steam engine, we're burning some hot coal, we're extracting heat from this kind of reservoir or like hot bath, and we're doing some work, we're powering a locomotive, we're getting something useful out, and then we're dumping some of that remaining energy into a cold environment, which is typically just the atmosphere. And now there's all sorts of interesting questions one can ask about such a setup. So for example, what is the efficiency with which you can transform this heat that you've taken from the coals into something useful like work? Can you convert all of it to work or only some of it? What is kind of the fundamental bound that's independent of what particular device or engine you try to build? And we can kind of move beyond just energy to think about other quantities flowing between systems. So, for example, if an ice cube is melting in water, there's energy exchanged, but also particles. So these molecules of water are going from what we kind of draw the ice cube into the water. And so now multiple things are being exchanged. And there's kind of many such examples in thermodynamics of these so-called extensive quantities. So that means they kind of grow with system size, which are exchanged between different kinds of systems. So to give you just one more example, if we think about an ideal gas, which is like an idealization of how gases in the real world behave, and it's a very well-studied model in thermodynamics. We can think about compressing a gas with a piston, and there we're reducing the volume of this gas while increasing the volume of the environment. So there's sort of an exchange of volume going on. And how difficult or easy it is to compress this gas is determined by its pressure. So there's this kind of intensive parameter, which the pressure doesn't grow with your system size. So the pressure at one point is the same as the pressure at another point. If your system was twice as large at the same pressure, it would still be the same pressure. It doesn't grow, even if the volume doubled. And similarly, for every extensive quantity, we have this associated intensive parameter. So for energy, which grows with the system size, we have temperature, which tells us how hot or cold the system is. And temperature is something you can just measure at a point in the system. It doesn't grow with the system size. And this kind of, all of these different pairs have kind of a similar function, even if the conventions for how we define these things are a little different. It's that temperature is kind of telling you how willing is a system to give up energy. So intuitively, a hot system is very willing to give up energy. And that has to do with something we can touch on later on, with how the second law works and how that tells us that the entropy of the universe always increases and never decreases. And similarly, pressure tells us if something is very high pressure, it wants to expand, it wants to gain volume. Something is very low pressure, it's more willing to be compressed and lose volume. So, giving you these examples like energy, particles, volume, all of these are things that you can measure, and they're things you can actually measure all at the same time. So if I have a gas, in principle, I could go in and count all the little molecules. I'd know how many particles there were. I could determine the energy as well. And I could just, measure the box and figure out the volume. So I could know these quantities simultaneously. And once this gas interacted with something, I could check how did the energy, the volume, the number of particles change. But in quantum mechanics, which is the theory for describing very, very small, very, very tiny constituents of our world, it turns out you can't always measure everything at the same time. So this sometimes goes by the name of Heisenberg's uncertainty principle. But one intuitive way to think about it is, for something so small like a little atom, how would you measure it? I mean, how do you kind of see the position of anything when you bounce light off of it and see what you receive back? So if you had a really small atom and you tried to bounce light off of it, it's actually so small that the very little like photons of light would actually disturb it. So maybe you figure out its position exactly if you send in some strong, very sharp light, very narrow wavelength. But then when that light bounces off this atom and tells you its position, it kicks the atom and it kind of disturbs its momentum. So you don't learn the momentum very well. On the other hand, you could use like a really long wavelength, really spread out and really gentle. So it doesn't really kick the atom too much. But because that wavelength is so spread out, you also don't learn the position to a lot of precision. And so this is just an example of this trade-off via the Heisenberg uncertainty principle, that there are different observables, different properties of a quantum system that you can't know simultaneously, can't measure simultaneously. So how does this connect back to our thermodynamic setup? We have systems that have multiple extensive quantities like energy, particle number, volume, and we want to probe them. But what if we study quantum systems where these conserved quantities, so things like the energy, volume, and particle number, are actually non-commuting? And non-commuting is one way of saying that they can't be measured at the same time. Now we're in a position where we want to figure out, okay, the system is changing, maybe its energy is changing, maybe the number of particles are changing, but can we actually probe those things at the same time? Well, we can't. So how do we go about studying these kinds of systems? Do their thermodynamics change? And does this teach us anything both about quantum mechanics, but also about thermodynamics? So that's kind of, setting the stage for where we come from with studying these like non-commuting conserved charges.
One introductory follow-up question to that would be what exact quantities we're interested in and if that matters for the investigation. So I think on the introduction here, we have this introductory figure that just displays a small system and an environment that are interacting or exchanging some information. And there's a note that the exchanged quantities are conserved globally, so we call them charges. Now, these
Mm-hmm.
charges that we're concerned with in the paper, what are we specifically referring to? Can we group a large amount or a large set of quantities into the same theoretical formalism and still be accurate, or do we need to make some separation as to what quantities we're actually considering?
Yeah, so some of the results are actually, fully general. So these charges could be whatever, really anything, so whatever observables you're interested in. It's completely generic. But what's always useful is to kind of connect some of this abstract theory back to real examples and also practical examples that one could actually implement in a lab and experiment on. And there, the very kind of typical example we use is the exchange of spins. So spin is kind of like a quantum version of angular momentum. So if we think about just classically a spinning top, it has an angular momentum. And this angular momentum is a vector that has three components, x, y, and z. When you go to the quantum case, you have a very similar picture where there's an angular momentum operator now that has x, y, and z components. And each of these components is an observable. So each of them could be taken to be the charge that we're studying. And these charges don't commute with each other. So the x spin doesn't commute with a y spin, and nor with the z spin. So that would be kind of an example as this kind of quantum version of angular momentum being exchanged or being the charge in question.
And how is that, conceptually speaking, being exchanged? How do two particles interact to exchange spins?
Yeah. So one way this could be done in a lab is, say you have like a trapped ion experiment. So you have two ions and they have some spin associated with them. You can actually interact them via turning on some coupling between them. So this, like in a lab, you have some controls with your like electric and magnetic fields, and you can control them in such a way that the two atoms will actually interact together and exchange this angular momentum so that it's conserved overall between the two of them, but it's exchanged back and forth.
Okay, maybe we can have a look at the example that's given in the paper, because I guess that's kind of what we're alluding to here.
Mm-hmm.
Would you mind describing what it is we're seeing in this introductory example and how that relates then to the topic at large?
Yeah. So this is basically very similar to what I was talking about, except instead of just thinking about two atoms exchanging spin, we're thinking about a little, we're kind of drawing the dotted lines differently. So we're saying two atoms together are actually our system, and there's a whole bunch of other atoms that are going to be the environment. But the quantity that's being exchanged is the same thing. It's just this angular momentum in the three directions, x, y, and z. And why this is kind of interesting is, in physics, people often study this notion of many-body physics. And what that means here is that you have lots and lots of atoms, and you're interested in some sort of effective behavior that becomes apparent when you have lots and lots of these small systems that isn't easily kind of discovered just by brute force analyzing the behavior of one system and then two and so on. But it's about finding useful and simple, effective descriptions of the physics of something with a lot of degrees of freedom.
Okay. If we look at the equation that's associated with this, there's a Hamiltonian that's described here by an equation where, as far as I understood it, these sigmas are exchanged locally and preserved globally. Could you elaborate on what that means in the context here? Maybe with the
Yes.
figure is easier.
Yeah. So you can actually go to maybe the Hamiltonian for a second.
Mhm.
Yeah. So basically what this is saying is it's kind of like the word is like a hopping Hamiltonian. So the way to think about it is this sigma plus and minus, you think about as either creating or destroying one unit of angular momentum. I'll be a little, vague about what one unit means, but in quantum, it's like angular momentum is discretized, and so there's like these kind of, finite number of chunks in which you can have it, unlike a classical top where you can smoothly change the angular momentum continuously. So, okay, so that's what like the plus and minus are. And the alpha just tells us in which direction. So are you adding or subtracting angular momentum in x, y, or z? So we can just say, let's just think about in the z direction for now. And the j in j plus 1 is just saying which atom are we talking about. So what this first term says is, it says, hey, look at atom j and actually add 1 unit of angular momentum there. But because it's multiplied by the other sigma, you have to do those two operations together. And that other piece with the minus now is saying take away a unit of angular momentum from the atom beside it, which is the j plus first. So in effect, what you've done is say, hey, take that unit of angular momentum, move it over to the neighboring atom. So globally, the total angular momentum hasn't changed. It just got moved over. But locally, it has been exchanged because now one atom has less and the other one has more angular momentum. And
Okay,
yeah.
please continue. Yeah.
No, and so that's all this kind of hopping Hamiltonian does, is that by the way we've constructed it, it moves these angular momentum between the different atoms, but
Mhm.
in such a way that in the total chain of atoms, the angular momentum is constant.
Mhm. And so the constant is important here because of the um, equivalence that we're trying to draw to the classical case with a thermalization process. We need to have a closed system. Is that the reason why we're putting an emphasis on having a preserved total spin
Exactly.
amount, if
We're
that's the right way of
interested.
formalizing it? Yeah.
Yeah, and it's sort of like we're interested in studying these notions of transport. So like how are things being moved here and there? But if
Mhm.
you didn't have, it wasn't conserved and like, energy was just being pumped in externally or spin was being pumped in externally, it's kind of difficult to track that effect as compared to the transport effect. And so
Mhm.
we're interested in these kind of closed systems to say, okay, there's nothing else going on. The spin is staying the same. Now, how is it kind of moving around within this closed system?
Mhm. Okay. One thing that I'm not able to wrap my head around just yet is we have a system like this, and we can manipulate these trapped ions if we have a quantum computer set up, for example, to, I suppose, exchange these spins as we would like them to.
Mm-hmm.
Are we not looking to study how systems evolve on their own naturally? Let's say we prepare a system in some state, and then we see what the thermalization process for that system would be, and we try to find specific cases where this non-commutation becomes a problem for that. It seems to me that we have a state here that we can manipulate in totality. What is the where are we actually? What are we learning from studying this example?
Mm-hmm. Yeah, it's a good point. So there's definitely one side of things which would be coming up with maybe like cool, maybe somewhat esoteric examples that in principle you can simulate on a small quantum computer because you can kind of simulate any quantum physics on a quantum computer. But it's also kind of important to look at examples that are more natural or that occur kind of natively, easily in different platforms. So
Mm-hmm.
with the example of this sort of spin being exchanged, it's true that you can implement like generically any Hamiltonian, but the spin hopping one is actually like a very natural one because it arises from just the natural interaction of these atoms with each other and with like an external magnetic field. So it's not as if it's something that's like very hard to implement or something, very artificial, but it's actually the spin exchange is actually a pretty natural physical phenomena, I guess, for this kind of chains. And it's something that's studied quite a bit, even outside of like this thermodynamic context, but for things like Ising models that describe magnetism for quantum systems.
Okay. And so, if we're studying the thermalization of the system, why is the degree of thermalization, I suppose, not well understood in this case? So, if this would be a classical system, we would know how it would thermalize. And my understanding is for a system like this, we don't have a clear description yet of how it would thermalize. But please correct me if I'm wrong there.
Yeah, I think there's basically one way to look at it is to say classically, if we're looking at thermalization, we have this kind of nice picture in phase space we can think about, and like ergodicity and mixing and these kinds of ideas that I won't get too much into, but just to say that like for classical systems, you're right, there's like a pretty strong theory and a good understanding of the thermalization of many systems. In the
Mhm.
quantum case, in this specific example, one thing that is a little strange is that we have a closed system which undergoes reversible dynamics. So the dynamics are implemented or kind of affected by a unitary, and a unitary is something reversible. So in principle, if I had like complete control of every degree of freedom, I could undo this unitary via another unitary, and I'd get back to my initial state. But this idea of thermalization is really associated with some sort of like irreversibility. And so there's this tension that says, okay, if I'm looking at a system thermalizing, where is the irreversibility coming from when it seems to be undergoing reversible dynamics?
Mhm.
And the way that's resolved is to sort of partition this large system into actually a small system of interest and treat the rest as an environment. And then what happens is now your system is no longer closed off because it's actually losing angular momentum or gaining it depending on what goes to the environment. And so while it's true that the system environment together are undergoing reversible dynamics, just on your system, you'll see basically an effective thermalization. But that's one of the challenges in understanding thermalization of quantum systems. And that's even independent of the non-commuting question, which we'll get to later, because so I mean that's sort of one answer. And now the second step with the non-commutation is to say, well, if you have non-commuting charges, what even is the thermal state you expect to thermalize to, and will you even get there in the first place?
Mhm. Let me toss that question back onto you then. So, in the scenario where we have non-commuting charges, what is the thermalized state that we're looking for? Or maybe a better question, how do we figure out what that state would be, or the set of states?
Yeah. So there was some work done sort of the last like few years about figuring out what this thermal state looks like, and it's sometimes called the non-abelian thermal state. Or non-abelian is just another way to say non-commuting or unable to be measured simultaneously. And it was actually found that like the form of this state is very similar to the form of the usual thermal state or Gibbs ensemble, where it's an exponential of some operators. So something like e to the and the way these operators are is it's each of them is an extensive quantity like I talked about. So like energy or a particle number operator or a spin angular momentum operator multiplied by the associated intensive parameter. So a inverse temperature or like a generalized chemical potential associated to a spin. So it turns out that the state takes a similar form, but deriving that form is a little bit more involved because not all derivations actually work. Some of them break down because they inherently assume that everything is commuting and that you need that for steps in the proof. But one way to kind of think about how any of these derivations go is to say, well, we start off by considering something in a microcanonical ensemble. So what does that mean? It means we think about something having a fixed energy. We think about a system and a bath, and together they're closed off from the rest of the universe. They have a fixed energy. And now we say, well, let's assume the bath is really, really large and the system is comparatively small. And now we say, well, what does the system's state look like? And one can argue in several ways, one being like a maximum entropy principle, to say that in order to maximize the entropy of the universe, the system alone ends up looking like a thermal state. And it's a thermal state where the temperature is set by the bath. So sort of ties everything together that, okay, overall system and bath have a fixed energy. There's no notion of a temperature per se because it's just closed, it's just energy. But when we kind of partition that into a bath and a system, now this bath we can assume is in some thermal state and has a certain temperature. And once we do that, it actually tells us what state the system is going to end up in. And now
Yeah, sorry. Just if I can jump in with a intermediate question there. If we're talking about maximizing entropy for a system at large, is that not a top-down computation inherently? I'm thinking you have a system and it's a closed system, and there ought to be, or well, maybe there are specific cases where this doesn't hold up, but the way I picture it is you have one constellation, one specific constellation for this entire system that maximizes the entropy of that system, and that would necessarily constrain also the subsystems. Are we saying that that is generally in alignment with optimizing a subsystem for maximum entropy as well? Or because to me it seems like those wouldn't necessarily be aligned, that you could have a maximum entropy system if you consider the system as a whole, where the subsystems are not necessarily maximizing entropy for the particular subsystems. Do you see the point, or do you see what I'm trying to ask? Okay, cool.
Yeah. So you kind of apply this maximum entropy thing in a way twice. First, what you say is you look at the system and bath together, and there's a fixed energy. And now you say, well, I mean, that energy can be realized in many different ways. So maybe one particle is moving really fast and the rest are a little slow, or they're all moving at a medium pace, and some are in the system, some are in the bath. I mean, there's a lot of what are called microstates that correspond to the same macro state. So in other words, there's very, two bottles of water can have the same temperature, but the molecules inside can be doing very, very different things. Or excuse me, the same energy, but the molecules inside can be doing very different things. And there's sort of this principle that if you don't know anything beyond the energy, you don't have any further information, then the best you can say is that any one of those states is equally likely. So given all the microstates that correspond to some energy that you know, you assume that the system and environment are just in a uniform distribution over all of them. So sampling one of them completely at random. You have no control, and they're all equally likely. But now when you look at just the system, this assumption translates into a thermal state just for the system. And it has to do with sort of a counting argument, because the most likely, there's kind of two competing factors that go on. If something's at very low energy, it's just more likely to be there at low energy because of a Boltzmann weight. So everything kind of wants to go to its ground state.
Okay.
On the other hand, as you increase the energy, there's more and more of these microstates that are accessible generically to a system. So you increase the energy, you say, well, there's many more states that are accessible, but the probability of being in any single one of those goes down. So there's these two competing elements that go on. One says, hey, let me decrease the energy and I'll be more likely to get, that's the most likely outcome. But then you actually have fewer and fewer states. On the other hand, you increase the energy and your probability of exciting all the way up there goes down. But there's just so many states that maybe it's okay. Maybe, you'll still end up in one of them. And so with these two competing elements, there's some maximum. So there's some energy that's not zero and it's not infinite, somewhere in between where you find that actually you have the highest likelihood of your system being in that state. And that energy and associated temperature is what determines which thermal state you end up with.
Mm-hmm. I want to circle back on something you said just before, in the midst of this explanation, that if we don't have any additional information, we assume sort of a uniform probability distribution across available states. I think that's the underlying assumption for statistical mechanics and the classical thermodynamical derivations. Is that argument still valid in the case where we have non-commuting charges?
Yeah.
Is it merely that we exclude some states because they're unattainable if we're measuring one quantity, but we cannot, or that we incur uncertainty in the other? Or is there some additional factor that would sort of play a role in that line of argumentation?
Yeah, I mean, you can actually do a very similar argument to say, let's say I know the spin in the x, y, and z directions. What state do I have? What's the state that, gives me those average values, just like I have the average value of energy, but it's sort of uniform over everything else. It's sort of maximal uncertainty about the things I don't know. And it turns out it is just this thermal state, this exponential of various operators, like a Gibbs ensemble or a generalized Gibbs ensemble. And actually, this is something that was studied even by E.T. Jaynes all the way back in, I think, the 50s in kind of a very seminal set of papers. So it is very similar in that sense, like as per one derivation, where things are a little bit more kind of at least on the surface seems like the derivation would break down, is to think about this example where I said you start off with a system and a bath together having a fixed energy. Now let's say we try to repeat that argument for our non-commuting case. We say a system and a bath start off with a fixed spin in x, y, and z directions. Well, already we run into a problem because you can't measure those things simultaneously. So how do we even set up the problem where we try to derive what the system's state looks like and figure out that it's a thermal state? And it turns out here we have to appeal to a very common trick in thermodynamics, which is to say we're only interested in very large systems. And by very large, we mean take the number of kind of particles or composite systems to infinity. What happens is when you do that, you can actually play this trick where even though x, y, and z don't commute with each other, when you look at the total spin of like a very, very large system, the amount by which these things don't commute, there's like a way to quantify that, is really small compared to the total amount of the spin itself. And so in a precise way, you can show mathematically that these things almost commute. And because they almost commute, you can actually you can just rerun this classical argument by saying, okay, they start off with a fixed x, y, and z, and you trace out the bath, or you discard the bath. You say, what does just a system state look like? And you end up with the same thermal state that you get via other arguments as well. So that's where the
And then you still
computation
go
comes from.
uh-huh.
Mm.
And then you still go on to study a small subsystem of that very large system.
Yep.
That's inherently what we're interested in. Okay.
Mm-hmm.
Um, Very good. So could we maybe talk about the eigenstate thermalization hypothesis as well? Because I think that relates to this discussion. If you wouldn't mind introducing that.
Yeah. So this is kind of a similar problem to what I was talking about by saying, well, we have a system, it's evolving unitarily, and so everything's reversible. But on the other hand, we expect that in some sense the system is thermalizing, and that something irreversible or something kind of locally thermal at least is going on. And so how do we reconcile these two different kind of competing intuitions? And that's something that, like the Eigenstate thermalization hypothesis, as the name suggests, it's a hypothesis, tells us kind of is a prediction for how these systems thermalize. And it's a little bit more specific. It says, you know, let's say we were trying to measure one particular observable, which we felt was like a good indicator of thermalization. What kind of measurement results do we get out of that particular measurement? So it's less about saying what is the state of the system sort of in abstract, and more to say specifically for a certain kinds of measurements, what would be the results that we get. And so actually I think there's a section of the paper that talks about it as well. But basically, this eigenstate thermalization hypothesis is saying that we basically get when we start off in a generic initial pure state and we time evolve the system and now look at a small portion and we look at some observable, the value we get is as if that small system were in a thermal state, up to some corrections that are small in the thermodynamic limit, which is making a larger and larger system.
And in the paper, we're then saying that there's a conflict with this ETH. Well, with this hypothesis.
Yeah, so
for
something that
these
is
systems, yeah.
being studied recently is this sort of non-abelian ETH. And basically so I guess one way to put it is to say the ETH is saying, okay, your system basically looks like a thermal state up to corrections that are 1 divided by the system size. So if your system size is like 100, you have corrections on the order of like 0.01, and the system size gets larger and larger, this correction vanishes, and for an infinitely large system, you'd really have exactly thermal expectation values. But what was found is in the non-abelian case, that correction term is actually a bit bigger. So instead of going like 1 over the system size, it goes like 1 over the square root of the system size. So that means you need a system of, like, let's say 10,000 atoms to get the same 0.01 correction. So for any finite size system, it seems like in the non-abelian case, there's actually more corrections to thermalization, or the system is somehow more reticent to thermalize in some sense.
And this conflict then is what leads to multiple stationary states being possible, or am I getting that wrong?
So I'm not too familiar with the connection. I mean, there may very well be a connection there. But I think even if you have a system with just a single stationary state, you can still find these like anomalous corrections. Um, yeah, so I think it's kind of like a different effect than the stationary state, multiple stationary states one.
Okay, okay. I want to scroll down and look at some of the physics that are implied by this. So I think there's a section here somewhere called New Physics. Here we go. First of all, we have some time average expectation value with a time limit here. Would you mind elaborating a little bit on what this shows and what it why it's important?
Mm-hmm. Yeah, so this is sort of the sort of one very kind of fundamental uh, I guess way of approaching things in thermodynamics is to connect these sort of time averages to ensemble averages. So the the two kind of setups are, one is I start a system in a very particular state, and what I do is I let it evolve for a long time, just exploring a lot of phase space, and every once in a while I'm probing it. So I'm looking at its energy or its whatever properties I'm interested in. And on the other hand, like a second kind of experiment, is I'm actually preparing a lot of different initial states, and I'm letting this like distribution, evolve for some time, then I'm stopping it. And now I'm looking at this new distribution of states. So just like a fixed distribution. And I'm kind of asking this question, well, how well does the first case, where just a single state is bouncing around exploring phase space, how does that connect to a second scenario where I just have no time evolution and I just have a distribution over phase space, different initial states I could have sampled? And this is something that's again studied classically, and there's very strong results involving like ergodicity and mixing to explain why it is that these two things seem to give very similar results. And this is sort of the one quantum version of that, where we're taking a state, quantum state psi, and we're evolving it over a long time. And as we do that, we're sort of probing this observable O, which is like whatever we're kind of measuring. And what we're seeing is, well, how does this time average connect to an ensemble average, which is what's on the right-hand side, where we prepare a thermal ensemble, a thermal state rho, and we say if we just prepare that, what would our expectation be for this observable?
Okay. And do we have some insights into what we would see? So if we time evolve a system like this compared to the ensemble expectation value, um, do we see a different picture here somehow compared to the classical case?
Um, I think so I'm actually not sure if you try to write down something classically, what this correction would scale as. Um, what's certainly evident is that there's a difference between the abelian and non-abelian cases where you have a different size of correction. So you can say that's certainly a quantum effect, is the bigger correction. Now, is this 1 over n term a quantum effect, or is that something that also can be, derive with some classical analog? That I'm not sure. I'm not sure.
Okay. Okay. I think one other point that's listed under the new physics is the hybrid energy level statistics. Would you mind just elaborating on what that means and why there's a difference in, well, why that arises in the non-commuting case as opposed to what we see in the classical counterpart?
Mm-hmm. So I will say I'm not very familiar with the work on the hybrid energy level statistics, but
Mm.
I think like a little bit. I think okay, so it's a manifestation of one general effect, which is to say, we've talked about the setup in the beginning that we want these charges to be conserved globally, but exchanged locally. And one way to think about that is it's kind of a constraint. So it says, if you try to come up with some sort of interaction between the different, with the systems, with the different atoms in the system, some of these interactions might actually not have the property that we want. They might create charge out of nowhere. They may not actually conserve it. So if you have some set of charges and now you say, okay, you have something that conserves them, and I give you even one more charge. I say, hey, here's another thing. It doesn't commute with the other charges, and I want this conserved too. It actually further reduces the possible interactions you can even write down. And so we have to keep putting more and more, basically each charge is more and more constraints on the kind of interaction that's allowed. And when these charges are non-commuting, these constraints are also even more stringent. And what that basically means is this interaction that we're talking about is going to be generated by some Hamiltonian. And so these constraints can be thought of as constraints on the Hamiltonian. So it kind of turns out that when you look at non-commuting charges, and now you look at what that kind of forces your Hamiltonian to look like, it changes the energy levels of allowed Hamiltonians in a specific way. And I'm not sure exactly what the results on that side are, but basically it's saying with non-commuting charges, the Hamiltonian is constrained in a way that changes its energies differently than in the commuting case.
Okay. And then I think there's Poisson-Wigner-Dyson dichotomy that refers to where states end up. So let me know if this is like out of your scope for the paper, but I think there are two distributions the way I understood it, depending on like what the statistical behavior of eigenvalue spacing is as a consequence, like in a particular system. And I think there's an extrapolation between those two distributions. That's how I understood it in the non-commuting case. Do you know if my understanding of that is correct, or whether there's something that should be adjusted?
I mean, definitely what you said sounds reasonable. Um, I think basically it's an idea that you can somehow tune from like a fully commuting case to like a slightly non-commuting and a slightly more non-commuting up to some sort of like maximally non-commuting scenario. And in doing so, you can study how these energy levels of your Hamiltonian change. And it's like a seemingly like a smooth sort of change from some sort of like non-chaotic system to a chaotic system.
Okay. In the section on new physics that arise as a consequence, is there anything you would like to highlight that I didn't touch upon yet, that you think is an interesting result of the study?
Mm-hmm. Well, we'll talk a little bit about some of the work that I've actually worked on like most closely recently.
Mhm.
And this has to do with studying these sorts of exchanges that we talked about, exchanges of spin and other quantities that you can't measure. And what we do is take kind of a different approach to answer this question of how can you actually probe these quantities that can't be measured simultaneously. So if you have two systems and they're exchanging spins in the different directions, you can't just track the x, y, and z spin at the same time, because if you try to go in and measure one, you'll disturb the flow of the other spins. So our approach is to say, instead of doing the usual kind of measurement in quantum mechanics, which is this strong, disturbing measurement, why not use a weak measurement, which is basically, as the name suggests, it's a measurement that is less invasive, and so it doesn't disturb the system as much. But as a consequence, you also learn less about the system. So what we do is actually build a framework that uses these weak measurements to probe the exchange of these non-commuting charges. And in doing so, we find that using quasi-probabilities, which are basically a generalization of probabilities that we see classically and that describe the classical world very well, we use these quasi-probabilities as kind of pretty useful quantum mechanical or tool in quantum mechanics to model this exchange. And what we show is that when you think about the entropy that's generated by the flow back and forth of these charges, it can actually depend on how exactly you choose to define the entropy for these quantum systems. And that three different ways to define it, which all agree classically, the three different formulas that all give the same classical definition, are no longer equal in the quantum case. Each one is a reasonable definition of entropy and teaches us something interesting about this charge flow process. So,
Do you have the time to very quickly elaborate on what the differences between the three are? If there's a quick conceptual
yeah,
way to describe
yeah,
that,
no,
yeah.
absolutely. So the way, one way I like to kind of categorize the three definitions is, so they're called the charge, surprisal, and trajectory definitions, is what we kind of call them. So the first one really connects to entropy's role in, let's say, conventional thermodynamics as this sort of extensive quantity. So when we think about the ideal gas example we started with, kind of started this talk with, there's energy, volume, particle number, and also entropy. It's like a fourth extensive quantity that you can use to describe this gas. And even just for steam engines, it's shown how does this entropy connect to the other three quantities in terms of their temperatures or pressures or chemical potentials. So this charge definition really ties back into that, and it recovers something very similar to a classical, like the fundamental relation of thermodynamics, which is like this dE equals TdS and minus PdV and so on. The second definition, the surprisal one, really connects to entropy as being a sort of information theoretic concept that captures uncertainty or your surprisal when you learn about the outcome of some event. And so this definition is kind of built out of measurements, and measurements, they teach you something, you gain some information. And so the surprisal definition kind of captures the uncertainty in this more information theoretic way, and it has an interesting result that it can actually sometimes be negative. So we find that the entropy generated can be negative, which is a little bit surprising because our scenario is just starting with two thermal states and letting them interact. And normally, when you just have two thermal states interacting, you kind of expect the entropy to increase. So our result is a little bit surprising, and it kind of connects there's a very pretty precise analogy with another interesting quantum result that came out in the last decade or so, which says that if you have two thermal states, but they're actually correlated, so they're entangled with each other, but locally they just look like a regular thermal state, then actually you can interact them, and you can also have negative entropy production because of the way you've set things up. So our result is something in a very similar vein, except we don't even need entanglement. We just use the coherences or these sort of superpositions in the initial state instead of entanglement. So basically we find that, okay, here's another quantum effect that can make the entropy negative.
Just one follow-up question on that. Maybe I or misinterpreted, but I had a discussion in the past where I think we discussed entropy. Well, entropy of the subsystems studied. Let's see, that the entropy of the subsystems studied in isolation, let's say, would become negative, but that would somehow be compensated for by the entropy associated with the entanglement of the particles. Is that is that what we're getting to here as well?
Yeah, I think that, so I'm not exactly familiar with what you'd been talking about before, but I think
Mhm.
maybe sort of riff off that, it's like this idea that the entanglement is sort of serving like a fuel, like a resource that's being burned up to reduce the entropy production. And because we still, we know the second law holds, we don't expect that to change for quantum systems. It's a matter of doing some kind of careful accounting to say, okay, it looks like the entropy of the system has gone down, but if you sort of think about the entropy needed to generate this entanglement in the first place, or generate these coherences or superpositions, you would find that, okay, like, you can't just win, you can't just make entropy smaller without some other trade-off.
And what would be the trade-off in this case?
So in the case of entanglement, it would be whatever you had to do to generate that entanglement in the first place.
Mm-hmm.
And similarly for
Okay.
coherences, right? Yeah. And so the third definition is what we call the trajectory definition. And this one is very closely related to entropy as this quantifier of irreversibility, or as generator of the arrow of time. So what we do is actually define entropy production in a way that it can actually have not just a real part, but an imaginary part. So it can be a complex number. And we find that this imaginary piece is only non-zero when there's a very specific kind of truly quantum phenomenon occurring, which goes by the name contextuality. But, for this talk, we just think about it as like something that's like certifiably quantum. So there's no way to kind of replicate the results you see in an experiment using some kind of classical model.
Okay, very good. Is there some situations where it's more practical to choose one definition over the other? If we're studying the system, is it clear which definition of entropy we would go with? Or is that a definition that's more of a matter of convention?
Yeah, and that's something I think we're still investigating a little bit. But it certainly seems like some definitions are going to be more relevant in certain scenarios. So, for example, if we want to study a quantum engine and we're interested in maximizing the efficiency of this engine, it seems like using the second definition with surprisal and some sort of measurement scheme might help us actually leverage this negative entry production to potentially enhance like the engine's efficiency.
Okay, very good. We are short on time now. I want to wrap up, but before that, I just want to ask a couple of questions. First, regarding the applications of these potential systems. Do you see any scenarios right now where these non-commuting quantities could actually be leveraged for something, yeah, for some kind of application?
Hmm. I think um, one interesting application is actually the sort of nascent quantum technologies like quantum computers or other kind of quantum simulators. Is understanding, can non-commuting charges help us in some way? So, for example, thermalization is for a memory, like a computer memory, a bad thing because it means you sort of lose the information that was in your memory. You just become the environment. You don't know what was originally stored there. So if we're finding that non-commutation, these non-commuting charges, are in some way resisting thermalization, it seems worth investigating if that could be actually used to build some sort of more robust quantum memory or more robust like storage for even like short-term storage for quantum computers in terms of how we encode the information. Um, I think more generally, the future as we see more and more development of like nanoscale technologies and really small devices that are utilizing and governed by quantum mechanics, understanding how to construct these kinds of like quantum engines, and especially ones that utilize non-commutation, we might find some of these results to be relevant there, but I think that's still like a little bit down the road technologically.
Mm. And then, very concretely for you and for this research, do you see any clear next steps that you would like to investigate or you think the community ought to investigate going forward?
Yeah, I think what's really interesting is looking at now more and more experiments and implementations of these kinds of examples. So we talked about the spin example, but I think it'd be nice to really have more examples beyond just this SU2 or this spin example, other kind of cool systems that are just natively non-commuting, and understanding, okay, what does the theory look like for these systems? What's new? What's different from just this spin example that we're so familiar with? And also, I think for me personally, one thing I've become really interested in is understanding this sort of like use of quasi probabilities to model these systems and to see how far we can take that. Just generally to think about, other quantum systems where we're trying to use quasi probabilities as a model, and to see like, is there a way to unify the sort of descriptions of these non-commuting and commuting charges in some way.
Okay, very good. If there are any final remarks regarding the paper, or maybe ask to the community or something like that that you want to raise, I'm happy to let you do that now. Otherwise, from my perspective, I'm happy with the interview here. So from my perspective, we can close it.
Yeah, nothing comes to mind. Yeah, just that, I'm always happy to talk to anyone who's interested about these non-commuting charges and quantum thermodynamics. Yeah.
Awesome. Thanks a lot then for taking the time.
Yeah, thanks so much for having me, Nicholas. It's a pleasure.